Live stream. Okay, got it.
Okay, I think we are live. Okay. Yeah. Hi, Sagar.
Yeah, hi, Professor Antek.
So Jordan, Michael, just to know, the Sega is our president for student, well, called GSO, graduate student officer. So she's going to host your next 30 minutes.
Okay, sounds good.
Yeah, morning,
The
Professor.
student part is going to be moderated and hosted by Sagar.
Okay.
Yeah, I think it's 10:30. We can start. Okay. Hello, everyone, and a warm welcome to the Fall 2022 edition of the Distinguished Theme Seminar Series organized by the Department of Statistics at Purdue University. This year's theme is Recent Advances in Statistical Inference. A big shout out to the Theme Seminar Committee for organizing this series. My name is Ontik Chakraborty, and I'm an assistant professor in the department. We have a few announcements before we begin the seminar. This seminar series is going to be live streamed on our department's YouTube channel. The URL is www.youtube.com/c/Purdue University Statistics. Before we begin the seminar, we remind those of you watching on Zoom to please keep your microphones muted at all times unless you are actively asking a question. If you are watching on YouTube, you can submit any questions you have in the chat and we will forward them to the speaker. Professor Jordan has generously agreed to have a 30-minute session with our students after the seminar. So students, please stay on after the seminar is over. Note that this session will not be live streamed on YouTube, so please use the Zoom link. Today, it is my pleasure to introduce our speaker, Professor Michael Jordan. Professor Jordan is the Pei Hong Chen Distinguished Professor in the Department of Electrical Engineering and Computer Science and the Department of Statistics at the University of California, Berkeley. He received his master's in mathematics from Arizona State University and earned his PhD in cognitive science in 1985 from the University of California, San Diego. He was a professor at MIT from 1988 to 1998. His research interests bridge computational, statistical, cognitive, biological, and social sciences. Professor Jordan is a member of the National Academy of Sciences, a member of the National Academy of Engineering, a member of the American Academy of Arts and Sciences, and a foreign member of the Royal Society. He is a fellow of the American Association for the Advancement of Science. He was a plenary lecturer at the International Congress of Mathematicians in 2018. He received the Ulf Grenander Prize from the American Mathematical Society in 2021, the IEEE John von Neumann Medal in 2020, the IJCAI Research Excellence Award in 2016, and the David E. Rumelhart Prize in 2015, and the ACM AAAI Allen Newell Award in 2009. He gave the inaugural IMS Grace Wahba Lecture in 2022, the IMS Neyman Lecture in 2011, and an IMS Medallion Lecture in 2004. He is a fellow of the AAAI, ACM, ASA, CSS, IEEE, IMS, ISBA, and SIAM. In 2016, Professor Jordan was named the most influential computer scientist worldwide in an article in Science based on rankings from the Semantic Scholar search engine. Today, Professor Jordan is going to talk about on dynamics-informed blending of machine learning and game theory. We are honored to have Professor Jordan joining us here today, and let's give him our full attention. Professor Jordan, please.
All right. Thanks for the nice introduction. It's my pleasure to join you today from a distance. So I think you have a wonderful theme and a wonderful group of speakers. I'm going to see if I can try to attend some of the talks as well. So the talk's going to definitely be about statistical inference, but in some sense, it's going to be more about decision theory. And decision theory is obviously, it's a Purdue specialty. And so I'm going to be contributing to the topic and really reaching back to the 40s and 50s in some ways where decision theory got started. And it was being done by mathematicians, statisticians, and also economists. And so game theory and economics ideas are going to play a role in my talk. And I hope to convince you that there are some emerging problems that can be faced in that topic. All right, so let's get started with this slide. In fact, I want to kind of hammer at that theme a little bit from the very beginning. This is an academic slide. I'm going to argue that economics needs to be brought closer to computer science and statistics for problems in the real world, in industry in particular. But academics are often reflecting what happens in the real world in industry. The term data science was an industry term that has been brought into academics. And whatever the new emerging discipline is, I do believe there is something new emerging. And it's an engineering-oriented discipline where you build things in the world and you use data and inference to build them and decision-making. And there are three disciplines that are contributing most to that, I think. Statistics, economics, and computer science. And interestingly, each one of them have had a pairwise interaction with the other disciplines in the past. Statistics and computer science, the blend of that is really, that's what machine learning is. Econometrics is a blending of statistics and economics. That's kind of the measuring of economic phenomena, mostly time series and causal inference. And algorithmic game theory is a field which emerged about 10, 15 years ago that blends economics and computer science, the algorithms of microeconomics. Now, interestingly, each of these pairwise blends is not very encompassing of the third leg of the triad. So machine learning doesn't have classically much to do with game theory and economics, and econometrics doesn't have much to do with computer science. Algorithmic game theory doesn't have a lot of statistics in it. And of course, the point is that in the real world, many problems have all three of these elements. You have statistical inference at the core, uncertainty, decision-making or uncertainty. You need to do it with algorithms. They need to be large and scalable. And you need to worry about the incentives of the people that are involved in the data analysis and the system that you're actually building. This isn't true of all problems, but I think it's true of many emerging problems. So the idea of just simply analyzing a data set with a computer, somewhat old-fashioned now. It's really analyze people's data and try to build services for people and link them in various ways. That's kind of the emerging class of problems I have in mind. Okay, so let's talk a little about this terminology, machine learning. Again, I think it's a blend of statistics and computer science. I tend to think of it's more statistics with some help from computer science, but that's my point of view. In any case, the last decade or so of machine learning has been focused on the field of pattern recognition. There are platforms, TensorFlow and PyTorch in particular, that have made pattern recognition into a commodity. And pattern recognition really is non-parametric regression, if you will, or classification. It's finding patterns in very, very large scale data sets and using that to build new capabilities, new even business models. And it's been such a success that there are people who argue that it's all you really need, that if you can do perfect prediction, really with very large scale data sets, you can solve in all kinds of inference and decision-making problems. And I'm going to argue that's not true. I'm going to argue that the decision-making side, really harking back to the 40s and 50s, is equally important, and it's going to be even more of a focus in the future. When you start talking about not just simple decisions like is there a bird in the image or not, but high stakes decisions. And when you worry about explanations for decisions and you worry about multiple decisions and multiple decision makers, there are many, many new problems that have statistical aspects to them that are emerging. So let's talk a little bit about decisions. And so I certainly mean decision theory to some level, but really I mean something broader than classical decision theory. So classical decision theory was setting a threshold in essence, and that's carried over to the pattern recognition literature, where setting thresholds on the output of a prediction system is kind of viewed as the entire chain of of statistical inference. So imagine, just for concreteness, that you're in your doctor's office in a couple of years, and your doctor is using a big prediction engine, a big neural network that's been trained with all the world's medical data to make the best predictions possible, better than any individual doctor. So you come in and they measure maybe 100,000 variables on you, including your genome or aspects of your genome. And that vector goes into this big prediction engine, and it's going to give out some outputs. And so suppose that one of the outputs is a prediction about your health of your heart. Do you have heart disease or not? And suppose that based on the historical data, a number over 0.7 suggests that you're about ready to have a heart attack and you better have an operation. And suppose your number is 0.701. Well, you're above the threshold, so the classical theory tells you, yes, you should just take this as a decision. You should go have an operation. But of course, in real life, that's not what you do. In real life, you start now a dialogue with your doctor. And in particular, what you're going to do is realize, first of all, you're going to ask about uncertainty. You're going to say, how sure are you of that 0.7 or 0.701 for me? Do you have confidence interval on that number? And I don't mean just a classical confidence interval, a Gaussian error bar. I mean, how sure are you of that number, really? So where did the data come from? Was it gathered recently, or was it gathered 10 years ago? Was it gathered on people like me or on a different population? Was it gathered using the same machine that's being used for me, and so on and so forth? So this is kind of real world statistics where data can be gathered over many, many years and a whole system can be built. And so a good doctor would have answers to those questions, and the uncertainty would wax and wane as you talk about these issues with the doctor. So it's not just that classical error bar with coverage guarantees. It's really about kind of, in some sense, perhaps Bayesian uncertainty. It's about how relevant was the data to a prediction, and so on and so forth. But then it's not just that. You could also realize facts about yourself that you'd forgotten or never even thought about. So you might say, oh gosh, I just remembered that I had asthma as a child. Maybe that's relevant here. Or I remembered that my grandparents had heart disease, and I never told anybody about that. It didn't seem relevant. And so now you realize that big prediction engine, that big neural network, cannot have all the world's medical data, because there's new facts that become relevant only in the moment. And this is true of any real world decision making. When you condition on the outcome of some test, new things become relevant that were not relevant before. And some of them are medical and some of them are pseudo-medical, and you're going to realize that this is, kind of the conditional perspective, that the context will change depending on where you are in the process. So just one big prediction engine trained on all the world's medical data doesn't really make a lot of sense. Moreover, there's going to be counterfactuals you're going to go through with the doctor. You're going to say, what if I were to exercise more? What if I were to eat differently? And so on. And a good doctor would be agile, would be thinking of that as new data to add to the original prediction, and updating and having a real dialogue about the situation that you're in. Okay, so that's kind of what a real world consequential decision looks like. It's not just thresholding a prediction. Moreover, that's just one decision. I'm making multiple decisions in my life today at different time scales. Some of them are quick in the moment. Some of them are a day-long process. Some of them are over months or my whole career. And they interact with everyone else's decisions, informationally, resource allocation-wise. And you realize that we're all embedded in this network of decision-making in all of the domains that we're interested in, and for our health, for commerce, for finance, for travel. And it's going to become even more so. We're kind of in this planet-wide information flows, and we're going to be using computers more and more to help with those flows. And that's kind of the right level of analysis for decision-making, really. And so now you start to talk about scarcity of resources and so on. You start to get into economics ideas already. All right, so to help make this yet more clear, hopefully, consider classical recommendation systems. These are matrix factorization systems. They're predictive engines. They take one customer's data and use it to make predictions about what some other customer might buy. But they're not really decision-making systems. They're simply pattern recognition systems. And in particular, if you start to see what happens when you make real decisions with these kind of these systems, you see that you can run into immediate problems. The original recommendation systems were used for things like books and movies by Amazon, Netflix, and so on. And it's become a huge part of industry, you know, very high productivity gains. So suppose you're recommending movies to people, and suppose that millions of people are now using your service, like with Amazon. You could easily recommend the same movie to 100,000 people, because each person, it's like a regression. Each person comes in, you treat that as an input, you make an output, and that's a recommendation. And you could recommend the same movie to 100,000 people. That's not a problem because movies can be copied arbitrarily. There's no scarcity. And similarly, true for books, you can copy books arbitrarily. And so you might start to think that there's no scarcity issues to worry about in prediction. Just predict and make decisions and don't worry about it. But you will see companies doing this for recommendations for things like restaurants, where instead of just having people browsing websites about restaurants, they actually try to connect up people to restaurants somehow. And if your app is being used by everybody in some city, you could easily recommend the same restaurant to 1,000 people. And if they all go there, you're going to create a line down the street. And same kind of thing happens if you recommend streets to drivers. The fastest street is well defined statistically, but if you recommend that street to everybody, you will create congestion, and it will no longer be the fastest street. How do you fix this? And the answer is not just to balance the load and to treat this as simply an algorithmic problem. You know, if I am, thinking about the restaurants I could go to, I have certain preferences. I might really want to go to a certain kind of restaurant. I may not even know my preferences in the moment. I might kind of think I'm in some new city. I might try a different kind of cuisine. I might be exploratory, and so on and so forth. So, and if you think of doing this at scale, you have 1 million people looking for restaurants in Shanghai, and there are 100,000 restaurants. There's all kinds of preference and utility issues that should come to play of making these decisions. You shouldn't just simply load balance. All right, so the alternative to thinking about a recommendation engine or a prediction system in this context is to create a market instead. So a market, for now, let's just think of it as a relationship between producers and consumers. You can have recommendation systems on both sides that help structure the market. So for example, diners on one side and restaurants on the other. And so a diner would broadcast their availability to the other side of the market, which is all of the restaurants. They would have their own preferences, and data about the restaurants and the diners would come into these recommendations, and bids would be made. And on someone's cell phone, there would be a bing, and they would accept the bid, for example, for a restaurant, and then that seat would be filled in the restaurant. So this is more like a matching system, not a recommendation system. All right, so matching markets have been widely studied in economics, so I'm just arguing that we should just do economics and forget about prediction. And the answer is definitely no. Microeconomics classically assumed all the preferences were known. They assumed that I knew of all the possible restaurants in Shanghai, I could make a ranked list of which ones I preferred. And every diner could do that. And every restaurant could say what kind of clients they prefer. And then given all that data, the microeconomics kicks in and runs a matching algorithm. So I hope you can see in the modern world that's just not feasible. It was sort of not feasible often. And statistics is needed to help shape this market. I need to experience some of the restaurants. I need to be related to other people. There should be a regression that kind of predicts which restaurants I'm going to prefer out of the ones I've never tried, and so on and so forth. All right, so this blend of statistics and microeconomics emerges even in a simple situation like this. Here's a situation that's a real world situation that I've actually been involved in. I'm also a musician and care a lot about the music world. In the data age, music is more and more popular than ever before. There are hundreds times more songs being written than ever before, and thousands of times more people listening to music than ever before. So you would think that there's a wonderful market here that is delivering all of this value to people. The answer is, of course, there's not. There's the legacy record companies who give huge amounts of money to a few people like Beyonce or Kanye West or whatever. And you might think that everyone's listening to their music. The answer is no, that if you look at the actual data, 95% of the songs being listened to today are songs that were written in the last 6 months, and they were written by people you've never heard of, mostly 16 to 20-year-olds. These kids are writing music on their laptop and they're really good at it, and they're putting the music up on SoundCloud and it's getting streamed to people, and the streaming service is endeavor to make money off of it. But they're not creating a market where the money flows back to the originators of the songs, at least not a real market. They give a little money back to them. All right, so this is a broken system. It's not an actual market. And so a lot of economic value is being left on the table. People can't have jobs making music, except for a very few who are making huge amounts of money. All right, so long story short, you can structure this as a two-sided matching market where data flows, who listens to what kind of music people prefer, like a recommendation system, are used to structure the market. People can learn who's listening to their music. So someone might see at the end of the week a dashboard and realize just by data analysis that they're popular in Columbus, Ohio, and they can go tell the venue owners there, I'm popular in your city. The venue owners can have them come give a show. They can make $10,000. If they do that 3 or 4 times a year, they start to have a salary. So United Masters is a company that's about 5 years old that has actually been doing this. And I'm on the board there working with Steve Stout, who's the CEO, a legendary figure in the music business. And he had this idea as well of a two-sided market, and we've built it. It uses statistics and data analysis, data science to structure this market. And it's not just a two-way market, it's actually three-way. The NBA and National Football League are actually part of the third side of the market. If the NBA wants to have a song accompanying some clip, then instead of getting that song from the record companies and Beyonce, they get the songs from United Masters now. And whenever a song plays, because you went and clicked on the clip, the actual 16-year-old gets the money. So it's really, there's 2 million musicians now on this website, and they're making actual money from this. They're starting to make a salary. So statistics can play a real role in doing this. This is not just statistics making data analysis more widely used. This is statistics setting up a new kind of industry and creating new kinds of jobs for people, 16 to 19-year-olds who otherwise wouldn't have had a job. Okay, so with that as background, I hope that you're convinced that there's real consequences for this kind of work. And now the question is, what kind of problems are there here for academics, for mathematically inclined people? And there are huge numbers. This is probably, in my at least career, the era in which I see more interesting problems than ever before. So just briefly, I'm going to get into some of these in the rest of the talk, but relationships among optima, equilibria, and dynamics. Optima are the things we study in statistics and machine learning, M estimators and gradient descent and so on. But equilibria are what you study in economics, things like Nash equilibria or Stackelberg equilibria. These are different kinds of points in various kinds of spaces, and they're linked in various ways, and there's dynamics that links them. And so working out kind of the rates of convergence of different kind of algorithms to approach equilibria based on optimization ingredients is very, very much open right now and very interesting. I've already alluded to the ideas of building multi-way markets where you're learning preferences, you're exploring to learn your preferences. Also, uncertainty quantification is really key here. You can't just simply put in optimization algorithms. You really have to have good quantified uncertainty. I've been working on this in the context of conformal prediction, but you're also going to hear from Rena Barber and Emmanuel Candes, who are colleagues who are working on that as well. So I've decided not to cover that in this talk. But I will talk about some of these other issues about mechanism design and contract theory, where we bring incentives to meet up with statistics. And things like privacy and fairness and social good, to my view at least, really require this incentives kind of structure of thinking about what's the social welfare of actual people, what are their utilities, and how does that interact with data and inference? All right, so here's the outline of the rest of my talk. I may not get through all of it. Let me just check my time here. But at least the first two, or actually first three, I definitely wanted to get through. Strategic classification, learning equilibria, and contract theory. So let me start with strategic classification. This is about a 5-year-old topic. This is work with Tiana Zernich and Eric Mazumdar, who are students with me at Berkeley. Eric's now a faculty at Caltech. So this is decision-making, back to decision-making again, but it's in the face of strategic behavior. Okay, so in many modern situations, you don't collect data just from the world and it's IID sampled and all. You collect data from people, and people are strategic agents. They have a vested interest in the outcome. So if you collect data, for example, to set health insurance rates, you're going to ask people to fill out some kind of a form, but they know that if they say that they're obese or they don't exercise enough or whatever, they're going to get a poorer rate. So they will shade the results a little bit. They will cheat, if you will. And so the health insurance company, of course, knows this, and they're going to ask questions which are a little bit hard to falsify. So for example, instead of just asking how much do you exercise, they'll say, can I opt into your cell phone for a day? I'm going to measure the acceleration, and I'm going to use that as a surrogate for how much movement you go through in the day. And there was actually a company, given that this is all really happening, that made a little device that you'd put your cell phone in, and it would artificially move your cell phone around, simulating exercise. So people are going to do this. This is just life. And if you don't face this, you're going to build classifiers that don't do a good job. They're going to have biases because of this feedback loop. This is well known in economics. It's often called Goodhart's law, that anything you start to measure that people care about, the measurement will get biased over time as people adjust their reports. So here's the poverty index score. It's in people's interest to appear poor. So from 1994 to 2003, the entire distribution shifted over from being Gaussian to being something else, because people wanted to appear to be poor. So the general problem is that we actually have feedback loops when we in learning and statistical decision making. So we have a collection of strategic agents. They're sending data to a decision maker who's building a predictive model. So think about loans in a bank. The agents are sending data. The bank is trying to make a decision whether to give someone a loan or not. Again, the agents want a loan, so they're going to shade their data a little bit to be able to seem better. Now, how do they shade their data? Well, they have to know something about the predictive model. Maybe they know it's a logistical regression, or they know something maybe a little more intuitive about it. And so the decision maker is probably going to reveal that information about what kind of model, either for regulatory reasons or just for good business practice, transparency. So now we have a loop where the agents will see the model. They will then send in data which reflects their understanding of how they can get good predictions out of the model. The decision maker will update the model and send that back, and so on. So in game theoretic language, this is a Stackelberg game, and it's one where the best responses on the two sides are statistical ones. Build a predictive model is the best response to data, and send data is the best response to predictive model. So it's a special kind of Stackelberg game. All right, so we can analyze it now as economists. We can ask, does it have equilibria, and are they good equilibria? And we can do that also as statisticians. How do we arrive at those equilibria? Okay, so classically in this game, classically is really only 5 years. This is not a long literature, but the decision maker is assumed to have all the power. They're assumed to be the leader. In a Stackelberg game, it's sequential. It's not like Nash equilibrium where it's simultaneous. Stackelberg, one decision, one agent, sorry, one side of the game acts first, and the other side sees that action and then acts second. And different equilibria arise depending on who's the follower and who's the leader. All right, so the classical analysis of this have assumed that everything runs in lockstep. It's a synchronous update. You have a model, you collect data. You have a model, you collect data. But in real life, loans or whatever, it's not going to be synchronous. There's no reason it should be synchronous. And so that's an interesting degree of freedom. The dynamics might change depending on who's updating more quickly and when they update relative to the others. So we have decided that we wanted to analyze this, and we have. So we've looked at decoupled timescales where there's no necessary linkage between the updates. All right, so we have two modes of decision making here. One in which the strategic agents are quick and the decision maker is slow. And we call this the proactive setting. Well, does that ever happen in real life? Well, definitely yes. So for example, college admissions, the college does not update its policy after every applicant. They wait every couple of years and update the policy for obvious social reasons. So this definitely has been happening in real life. But what about the other direction? That the decision maker is really fast and the agents are slow. Well, this happens, of course, in things like YouTube. YouTube collects data all the time and is always adapting the model depending on the clicks and the patterns of the agents. Okay, so we have these two kinds of dynamics, and now the question is, what properties do these have? In particular, are their equilibria and what do they look like? All right, so I'm going to briefly give you some results and then I'm going to move on. There's a paper on this on the archive if you want to see some more details. So first of all, we're able to analyze this as economists. We're able to show that you do have Stackelberg equilibria here in either order of play. That's not so surprising. Much more surprising is that for these statistical games, it turns out that both players prefer the equilibrium where the strategic agents lead and the decision maker follows. Okay, so this is interesting. It's somehow not surprising that the strategic agents prefer to lead here. And it's actually been known that when the decision maker leads, the decision maker gets a very good, or they gets a relatively good result, and the strategic agents get a very poor welfare. So if you flip it around, you might think the decision maker is going to be unhappy now, but that's not true. And when the strategic agents lead, the decision maker is also happier than they would be when they lead. Okay, so this is not true of general Stackelberg games, but it is true of these statistical Stackelberg games. It's a special set of games. And these are, when I say statistical Stackelberg, I mean under certain assumptions, in particular generalized linear models. Okay, so let me move on. I'm going to go over, I think, 3 more little vignettes here and give you really more of a flavor. What is the problem, the challenge? Where is the statistics and where's the economics? How do they come together? And then I'm not going to give too many details on the actual mathematical solutions. This is with Lydia Liu and Horia Mania at Berkeley. So we're trying to bring together bandits, which is a learning idea, a decision-making idea, and matching markets, which is microeconomics. Okay, so I hope you all know what multi-arm bandits are. This is an exploration-exploitation trade-off methodology. So someone is trying to decide among a set of actions, which action do they pick? They don't know which gives the highest reinforcement or reward, so they just try them at the beginning randomly, and over time they start to make a model that is usually a minimal model, just at a confidence interval on the mean reward. And the algorithm is to pick the arm that has the highest upper bound of the confidence interval for good reasons. And this is an optimal algorithm, that the regret that you have is logarithmic in the number of trials. Regret here is how well do you perform in terms of average reward relative to an oracle that knows the best arm a priori. Okay, so that increases sublinearly and particularly logarithmically for this algorithm. All right, so that was the game, sorry, the learning side. Matching markets, I hope you all know what these are as well. You have buyers and sellers, and you want to make a matching. You assume a priori that you know the preferences, so that buyer 1 prefers seller 1 to seller 3 and seller 3 to seller 2, and then all buyers and all sellers write down their preferences. And then there's a famous algorithm due to Gale and Shapley that is called deferred acceptance, that finds a match that has a stability property. Okay, so obviously you might want to put these 2 ideas together. What if I have matching markets where you don't know your preferences a priori and you have to explore to decide which of the other side of the market you prefer? Okay, so let's imagine we have not just one agent, but we have competing agents. Here, a bear and a human, and they're both trying to pick a preferred action on the other side of the market. If they both happen to pick the same arm, that's where you have now a conflict, and you have to say, how am I going to resolve that conflict? And so in our model, we have scarcity. So what we assume is that the bear, that's one of the agents gets the reward, and the other agent does not get the reward, gets no reward. So who gets the reward? Why did the bear get the reward? Well, arm 2 has its own preferences back on the left side of the market, and so it, for some reasons, prefers the bear. The human sees this, and they say, oh, even though I like arm 2, I better explore more than I otherwise would, because the bear seems to like arm 2, and if the bear picks it, I lose. So they explore more than they otherwise would. That means they have a higher regret because of the competition. All right, and so one wants to now do the mathematics to see what kind of regret you get in this matching market version of bandits, and is it worse than the single agent case, and how much worse? All right, so again, I'm not going to provide details here. Let me just skip over this. This kind of sets up what is a bandit market. This is a definition of regret. It's the reward that you have relative to what we call the stable match reward. It's if you knew the preferences a priori, you gave them to the Gale-Shapley algorithm, that would form a matching. How well do you relative to that? All right, and we are able to prove a theorem that says that the regret for a natural class of algorithms is actually still logarithmic in n. Okay, so you don't lose in terms of the regret as a function of time, but what you do lose is there's a new term in the denominator, this delta squared, which is a measure of the overlap between agents. If you have a small gap, then that number is small, and that makes the regret get higher, but only as a constant. Okay, it doesn't affect the log n factor. So competition does affect performance here, but only as a constant. All right, so there's now a literature building on this. This is about 3 years old. I want to mention one of the papers that has come out subsequently that kind of starts to make this more into a general theoretical discipline. So the general problem here is learning equilibrium matching markets from banded feedback. And this is work with a bunch of colleagues at Berkeley, Mina, Alex Yishing, who's now in Michigan, and Jacob, who's at Berkeley. So the general problem here is that we're not trying to optimize, we're trying to find equilibria. And we're going to do this now in the more general problem of what's called transferable utilities, also called the Shapley-Shubik model. Here's where there's payments that goes between the two sides of the markets. So this is more like Uber, where there's a driver and a rider, that's the two sides of the markets, and there's a payment that goes in between them. Payments give you more flexibility, and it's a more powerful model, and it's somewhat harder to analyze. Okay, so what we've done here is to introduce a new measure of instability. And in economics, stability is kind of a 0-1. Either you're stable or you're not. As a statistician, I'm not happy with that. I want something more quantitative. How unstable are you? Can we do gradient descent or something to make ourselves more stable? And so we figured out a way to do that. And here is our quantitative measure of instability for general transferable utilities. And I'm not going to get into this in any at all, but it's explained in our paper. And it is kind of a Shapley index kind of thing, if you know what that is. You compare the maximal utility you can get under one matching to the utility you get under another matching, plus the tau variable is the transfer, the monetary transfer. And then you take a maximum over all subsets of the agents. That's very much in the Shapley spirit. This also has a VCG flavor if you know about auction theory. Okay, now it turns out that this, if you treat this as a primal problem, this maximization problem, and you take its dual, the dual has a very nice economic interpretation, which is that the measure of instability is how much money does an external agent have to add to make the current system stable. Okay, so it's unstable, but if I were to add money to the problem, then I'd have more wiggle room and agents would find a matching and I would become stable. So the minimal amount in the dual problem is exactly that measure of instability. All right, so you can now optimize this quantity and do statistics with it. You can take a network and you can estimate to optimize this measure, and you can also do decision making to optimize this measure. All right, so it turns out if you apply this back to the Liu, Horia, and Jordan paper of the simpler bandit matching, that this framework gives you exactly that logarithmic regret that we had done in bare hands in the previous paper. All right, so this general stability measure, we think is kind of the right way to think about statistical version of matching markets. Okay, I think this will be the last part of my talk. This is about contract theory. So these are about incentives, and I'll explain what contract theory is, and I'll explain what our statistical version of contract theory is. So this is with Stephen Bates and Jake Stoloff, who are at Berkeley. Actually, Jake has now moved to Chicago, and Michael Sklar, who's at Stanford. All right, so let me take a little breath here and let you all reset for a moment. All right, so incentives are really, as I've alluded to, critical in trying to understand how agents in the real world will react to data analysis situations and how they will expect to get something good out of the data analysis and not simply be passive providers of data. All right, so we've kind of alluded to incentives in the previous two parts of the talk, but we really haven't focused on it full on. All right, so now I want to focus on it. There are books on the theory of incentives in economics. The theory of incentives has kind of two main branches to it. One is called auction theory. It's the theory of how you run auctions. Something like Vickrey auctions are studied there. And the other branch is perhaps less known by people outside of economics. It's called contract theory. All right. So in contract theory, this is an asymmetric situation. It's very natural to a statistician. You assume that there's agents, they possess private information, and there's a principal who wishes to incentivize them. Okay, incentivize them to do what? Well, take some actions that depends on the private information without revealing the private information. All right, and the goal is overall social welfare or perhaps revenue. All right, so you all already know what this is. On the airline, there are business fares and there are economy fares. So every airline does this. And you probably have thought about that a little bit about why do they do that? And the reason is because of contract theory. And so if you think about it, let's suppose we were trying to set a single price for the entire airline or airplane. All right, well, if we set the price too high, of course, we won't get a large number of people who just don't want to pay that high of a price. So we set the price lower, but there are some people who maybe have a lot of money or they just really need to get from one place to another. They would be willing to pay quite a bit more. And we lose the difference. We lose that money that we could have gotten if we'd set a higher price, right? And so if we set the price, at a certain level, good enough to, get those higher people and maybe get a little bit of the people who are less willing to pay, we will probably not have a full airline, right? So what you might like to do is just ask people, hey, how much are you willing to pay? And that's somewhat like what auctions do. Right. But people aren't going to engage in an auction. They're certainly not going to just tell you about how much they're willing to pay. So contract theory is the way to go at this. What you do is you say, I'm going to set up a menu of options, a contract. And in that menu is a service and an amount. So the service is there's this thing called business class. And in business class, you pay more money, quite a bit more money, but you get a free glass of wine and you get to go on the plane earlier and you have a slightly bigger seat. And now to a lot of people that would sound silly, they would never do that, but there are people who are willing to pay a fair amount of more money for those little bits of special treatment. All right, and so everybody else pays a lower amount and they don't have any of these services. Now, everybody has the option to choose either one of the two services. Someone who's willing to pay a lot could still choose an economy fare. But what happens is there's a certain number of people who self-select without being asked, and they pick the business fare. And so the airline gets their money, and the remaining seats that aren't been picked by those people can be filled with people who take the economy fare. All right. So anyway, I've gone on a little bit too long on that, but this is a whole branch of economics, and there is a whole theory on how you set up contracts for all kinds of situations. So we're going to bring this into the world of statistics. So in particular, let's imagine a statistical testing situation where there's the Federal Drug Administration, that's the principal, and there's a bunch of agents. Those are the drug companies. The drug companies would like to, they've developed some drug and they'd like to have their drug go on the market. All right. The FDA doesn't want to put bad drugs on the market, so they're going to test this with clinical trials. Okay. We exactly have a partial knowledge situation here. The agent knows something about their drug. They developed it. They used their scientists. They probably did a little internal testing. They have some rough idea if it's a good drug or not. They're not going to simply tell that to the principal. All right. So the principal is operating a little bit blindly here, and they're trying to incentivize people to send their good drugs and not send their bad drugs. All right. So, obviously clinical trials are important, and a statistical audience, I don't have to emphasize this, but it's really many tens of millions of dollars per year investment in running large-scale clinical trials. So you clearly don't want to be running too many clinical trials on lots of drugs, which are not very effective. You'd like to focus in on the better ones and put your resources there. All right, so as a statistician, how do you do this? How do you set up such a testing protocol? Well, you start with Neyman Pearson. So for example, let's suppose there's two kinds of drugs, bad drugs and good drugs, theta equals 0 and theta equals 1. And bad just maybe mean not effective. And you set up a test, a thresholding procedure, perhaps such that for the bad drug, the false positive rate is 5% and the power is 80%, kind of standard numbers. Okay, so that's certainly doable based on some data. And all right, but now the question is that a good statistical protocol? Okay, it's optimal in the Neyman Pearson theory, but is it actually good in this world? So case one, suppose that it costs $20 million to run a clinical trial. And suppose that if your drug is approved, you make $200 million. Okay, so not untypical numbers. All right, now you can do a little calculation with that table and those numbers, and you can find that the expected profit, given the drug is actually a bad drug, theta equals 0, is minus 10 million. All right, so the drug companies can do this calculation, as can the FDA. And the drug companies do it, and they are not going to send lots of their drugs because there's a negative expectation. Okay, so they're probably only going to send drugs if they're pretty convinced internally that it's a theta equals 1 situation, not theta equals 0. Of course, no one really knows whether it's theta equals 1 or theta equals 0. This is statistical, right? But they're going to send the drugs where it seems most likely that they have a theta equals 1 situation. On the other hand, in case 2, let's suppose that it costs you $20 million to run a trial, but you make a profit of $2 billion if your drug is approved. Okay, so you do the same calculation again, and you find out that your expected profit is 80 million, even if you don't have an effective drug. So now you're just going to send all kinds of drugs to the FDA, hoping for a false positive, right? Because if it's a theta equals 0, and the FDA approves it, that's a false positive, but that can certainly happen. And then you make $2 billion. And of course, eventually people realize it's not a good drug and some other drug will take over, but you made $2 billion in the meantime. All right, so the FDA is very much interested in not having this, all these bad drugs sent. They want to incentivize people to send this, but it's not the case. They can just design a statistical test to do this. So this is where you want to do something like contract theory. Okay, so again, I'm going to give just a little bit of the results here. I hope by setting up the problem, you've gotten interested and you'll maybe look at the paper. So what we've done here is that we've set up a new kind of contract, which has statistics built into it. So here's what an agent sees. They have an opt-in protocol. Either they can decide not to do this protocol at all, in which they pay nothing and they send in nothing, or they can opt in, and the first thing they do is they pay our dollars. All right, then they choose a payout function, F, from a menu of options. This is just like business class or economy class. All right, so they will choose it based on their internal knowledge of, what how likely their drug is actually a good one. All right, now having chosen that payout function, a statistical trial is run. That yields a random variable Z, which depends, of course, on the true theta. The agent now receives a payoff, the 2 billion or the 20 million or whatever. That is a function of the statistical trial, right? Whether, you had a good result or a bad result. On the other hand, the principal receives a utility, which depends on f of z as well, but also depends on the theta, the true value. Was it a good, bad, or good or bad drug? Because the FDA is going to get negative or bad utility if they approve a bad drug. Okay. So that's the contract. This is contract theory, but again, inside of the box is not usual contract theory stuff. There is, testing kind of machinery. All right. So in the next 2 slides, I'm going to show you the results we've been able to get, and I'm not going to give details, but hopefully it'll make some sense. What we want to do is transact only with the good agents. And so we define a contract to be incentive aligned if, when you take an expectation over this testing randomness, the amount you win, f of z, minus the amount you paid, r, is negative. Okay, so that's the agent's expected profit. And so we're designing this menu. We want to make sure this is true. Otherwise, the agents are having arbitrage. They can make money from nothing. Okay, so we call that incentive aligned. All right, so this incentivizes agents to drop out if they have drugs that aren't any good. Okay, now that's our contract theory. What about in statistics? All right, so I'm going to define an E value. I think a lot of you know what that is. It is nothing but a random variable. And it's an E value for the null hypothesis if its expectation under the null hypothesis is less than or equal to 1. Okay, so this is akin to a P value, which is a tail probability under the null hypothesis. And this is a random variable that has an expectation that's being controlled instead of a tail probability. So E values have been studied for other purposes in statistics. And it turns out that these are exactly the right quantities to be using for statistical contract theory. So we have a theorem that says that a contract is incentive aligned if and only if all of the payoff functions are E values. All right, so that really, in some sense, is a Neyman Pearson style theorem. It sort of tells you what kind of procedures you can use, you should use, if you want to have a good statistical contract. All right, and from there we are able to then go to the full decision theory. We do, we don't know theta a priori. So we set up a maxi-min optimality story, which is we put a distribution over Q, and then we want to, under the infimum over that distribution, find the contract which maximizes that expected utility. All right. And again, I'm not going to give details here, but we were able to prove that a menu is maxi-min if and only if it's in this subset of incentive aligned contracts. Okay. And that also tells us as a corollary, what are the optimal contracts? They are all E values in a certain situation. All right, we are using this now in some applied problems. And just briefly, this is the one called federated learning. This is a hot topic in machine learning. These are from a couple of blogs. It's a problem where you have a server and that is trying to build a central model, and it's got lots of local models, perhaps self-driving cars or other local agents. They have local data. They send that to the server builds a model and sends that back to the agents. All right, so this is being done mostly without any notions of incentives or economic story about the data. And so here on the NVIDIA blog, you have hospitals, research centers, and cancer centers. And you sort of can imagine this is not really going to work if you don't start to think about incentives. Okay, so we have looked into this, and we have a paper now just came out this summer where we are using our contract theory to actually apply it to this federated learning problem. And the key tool that links the two here is what we call statistical accuracy shaping. And I won't get into that, but if you're interested, that's the extra little bit of mathematics which is needed to link the contract theory to the federated learning. Okay, so I'm done. I have gone through everything I wanted to go through. I could go through more, but I think that's plenty. I've tried to give you examples. I've given you 3 examples. I skipped the auction theory, where these 3 disciplines come together in a foundational way. It's not just a little bit of a econometrics added with some computation or machine learning with an extra economics. It's really problems that demand all 3 of them at the foundational level. And I should say that this is an academics picture, but when I spend time in industry, which I have been doing for years, I see real world problems being solved. For example, where you have some kind of a service that people are engaged in, you want to be fair, you want to have prices, you want to serve the long tail, and you want to have this be scalable, that you have people from all 3 of these disciplines around the table. You rarely have these problems being addressed by someone in just one of these disciplines. And I should add, I don't mean only these 3 disciplines are the important disciplines going forward for this emerging field. Certainly operations research is in this mix, control theory, and then various areas of the social sciences and law and so on. And of course, there's support from various branches of mathematics and so on. But I do want to highlight there's kind of inferential thinking, there's computational thinking, and there's incentive thinking, that those 3 styles are coming together. That's really what this is about. All right, and then this is my last slide. This is kind of going back to the very top level. A lot of people are talking about machine learning and AI these days. And it took me a long time to kind of realize what I think it is. I don't think it's a new academic field, either of them, at least machine learning. And AI is really being used to refer to machine learning these days. It's really just statistics, you know, with maybe some more additional algorithmic support and additional depth in certain topics. But it's a kind of statistics which aims to build real world systems and solve large scale real world problems. Statistics has never really kind of taken on the agenda of building an engineering field, of trying to build systems out in the real world. At least that's not been its main focus. The main focus of statistics is the mathematics and the science. But this is not new in history. So chemical engineering, before the 40s, 50s, there was no such field. There was chemistry, and there was fluid mechanics and so on. And it was clear what would happen in a test tube if you put certain molecules together. But the idea that you could build a factory and bring in large quantities of stuff and it would actually interact and create product at scale, that was a brand new thought and idea. It required new concepts, new thermodynamics at scale, new fluid dynamics at scale, and so on. So people built these systems, and at the same time, a new academic discipline emerged that eventually got called chemical engineering. Electrical engineering, I know less about the history, but before electrical engineering, there was certainly Maxwell's equations. So a scientific understanding of electromagnetism was at hand, was known. But to electrify a city or build circuits or bring power into a person's home, you had to think about new tools. A lot of Fourier theory got used and so on. And this field called electrical engineering emerged. So I think that's what's happening in our era right now, that people are building on inferential, the existing theory from statistics, inferential ideas, algorithmic ideas, and economics ideas, but they're building new kinds of systems like, Uber or Amazon or healthcare systems or finance systems that are blending statistics with economics with computer science, but doing so in ad hoc ways, just like the original people building factories in the 40s and 50s. A lot of those factories didn't work, or they exploded and hurt people and so on. And so I think that's kind of where we're at now. We have an emerging field, which is having a lot of power, but which is still very immature and very much in need of foundational perspectives. So I'm finished, and I'll be happy to take questions in whatever format you wish.
Thank you, Professor Jordan, for this excellent talk. Any questions from the audience? Or YouTube? People on YouTube, again, you are encouraged to submit your questions on the chat.
So, can I start, Professor Antik?
Yeah, if there are no questions from the general audience, I'll since we have 5 minutes left, I'll take a couple of minutes before starting the student sessions, just to.
Sure. I mean, yeah, I have got some questions from students.
Oh,
but this
yeah,
was
yeah,
my
yeah.
question.
Yeah. Go ahead.
Yeah. Thank you, Professor Jordan. So you discussed about the human and bear example, right?
Yeah.
Yeah. So what if there were there are on the right hand side, instead of arms, there were a couple of restaurants, and on the left hand side there are multiple humans who are trying out restaurants. So how does that setting match when there are when an arm can cater multiple people?
Yeah, no, I mean that's easy. That really, we're just modeling scarcity. Your protocol can be that the restaurant has got 20 seats in it. Okay. And if 21 people choose that arm, right, then the restaurant picks 20 of the 21, right? So that's certainly easy. Okay. But more interesting question is, are there recommendation systems being used on both sides? So for example, when I go into this system as I'm walking around in Mumbai, say, and I maybe have never been there before, and I don't really understand the lay of the land. I don't want to go to a search engine and start looking for good restaurants in Mumbai. I'm gonna get a lot of nonsense. And I don't want to do that search demo. So what I want to do is push a button on my phone and geolocate me, and then know something about me, that I like fish, I like spicy food or whatever, and I have a certain price point, and know some facts about me, and then transmit that information to the other side of the market. And the other side of the market is all the restaurants, and they're looking not just at me, they're looking at maybe 100,000 clients in that moment, and they have their own preferences. Maybe they prefer people from out of town or people that have been there before or whatever. And on both sides, you share information. When I go there, I'd like to have knowledge from other people who've gone to Mumbai or who like me. And so I'm in a social network, but the restaurants are also linked in maybe a more competitive network. And so that entire market has got recommendations on both sides, and it's got exploration, exploitation trade-offs, and it's got matching. Mm-hmm. All right, and it's got these limitations. You can't send too many people to one restaurant at all. But I think that the market and meat statistics way of thinking about this accommodates, multiple aspects of this. And the people that work this out, I mean, there's already kind of companies that start to do this, like in the music example. It's not, it's not a complete mystery to how to think about building such systems. And what I just want is, like in the chemical engineering setting, I want kind of the mathematics to be there to support this kind of building.
Sure. Thank you, Professor Jordan.
Yeah, can I ask a question?
Yeah, sure. Go ahead.
Yeah, hi, Professor Jordan. That's a very nice talk. I have a question about the matching part. So in the matching part, you define a regret, and then so would that be, there are two objectives. One is to minimize the regret. Another one is to estimate the parameter. So would that be these two go to be conflicting with each other, and do we need to trade off these two?
Well, yeah, normally you don't care about estimating the parameter. Really, this is decision theory. estimating the parameter is just a way on the way to getting a good decision. And so if I can minimize the regret, which is really a challenging thing to do, that's really what I want to do. Now, regret can be one of many things. Regret always has an oracle. It's regret relative to some oracle, and you get to define the oracle. Right? Is the oracle like the best decision in hindsight? Is the oracle the best decision where you're allowed to switch a couple of times? And so on and so forth. Then we have this notion of stable regret. We have a pessimal stable regret, then an optimist stable regret. So I really love the regret framework. It allows you to have a lot of flexibility, and I don't really care about estimating a parameter in a lot of these situations. I want to make a good decision.
Okay, yeah, thanks. Maybe a follow-up question is that in that case, so in the first paper you mentioned, you use the ETC algorithm to estimate the parameter. In practical setting, will commonly feel comfortable to just randomly explore and randomly match people? And do you have
though there's a lot of work on the bandit literature on the relative optimality of just random exploration versus UBC algorithm or versus other algorithms. And let me just say the random algorithms are much poorer. The UBC, the confidence bound or Thompson sampling algorithms are much better. But I think that's only the tip of the iceberg. In real world domains where there's 100,000 restaurants, the random exploration is not a very good idea. Okay. And so if I go to Shanghai or whatever, there's a lot of restaurants, even more than Mumbai, I think, and I don't want to randomly explore them. All right. So instead, I want to have, say, a Thompson sampling algorithm where I'm part of a group and similar people. I share statistical strength with people in my group. And so I'm kind of already biased towards a certain set, and then Thompson sampling also permits that I just kind of somewhat randomly try out a new restaurant always. So yes, I think structuring the decision space with those kind of things is a better way to get exploration. And we're trying to do that in the context of matching.
Okay. All right. Thank you very much.
Okay. There's a couple of questions on the chat. We'll go through those questions and end the seminar, and then we'll have the student session. So the first question is from Aileen Fay. The question is, where do you see the direction of future research in this area going?
Yeah, so I mean, my talk had several sub areas in it, and they're all kind of very active right now with probably every day on archive, I see about 5 new papers on each one of these things. So it's a little hard for me to say. I would encourage you to learn about the EC conference. If you don't know about this, economics and computation, you'll see a lot of work on auction theory, on contract theory, on information asymmetries, on incentives and all. And they're becoming increasingly aware of statistical ideas. And let me just say that, this is also not that new. David Blackwell is an example of someone who was working simultaneously in economics and statistics and computation. And David would certainly have agreed with, this perspective. This was really his in many ways. So what I think happened after David is that, David and Ken Arrow and a few others kind of did this kind of work, and then it kind of got split off. The statisticians went and ran off their, looking at their problems, asymptotics of linear models, generalized linear models, and the economists went looking at their problems, and computational people went after some certain problems. But it really needs to come back together. And I guess that's what I'm really more, kind of emphasizing, is that the Blackwell perspective for 40, 50 years kind of has only slowly progressed, but now the real world is catching up, and we're kind of returning to that more unified way of thinking about research.
Okay, the next question is from Yondong Lee. So the question is how to evaluate the matching result besides regret in the real scenario, such as school admission. How does the school evaluate their recruitment in the last season?
Yeah, that's a great question. And so this Yuan Tong is asking to how you really do this in the real world, and it really matters. And since I'm not an expert on admission markets, I don't really want to say. Also, there are kidney exchange markets, as you may know. Those are another examples of matching markets, which has had it's saved hundreds of thousands of lives, where you match someone who needs a kidney to someone who has a kidney within the same family, and it's an interesting complex system. Real world matching markets also have things like 2-body problems, right? I want to go to a certain school, but my wife also wants to go to the same school, and the school wants to take that into account. And so it gets more and more rich as time goes on. And so the right way to think about this is that there's not going to be just formulas that you apply to these situations. We're going to train a new generation of people who can think this way, who can go out in the real world and say, oh, that's the problem. I need this bit of statistics. I need this bit of matching. I need this bit of thing. And I'm going to be like an engineer. I'm going to, do it in the right way. And then I'm going to have, testing and evaluation procedures that allow me to say, did I do a good job? And how do I check that I did a good job? How do I do auditing? This is, like I say, an engineering discipline like chemical engineering, whatever, has all of these things. It has auditing. It has checks about, is the circuit really a good one? It's not going to burn down the house. It has a whole infrastructure around it. And so I think we've been kind of, because in statistics, we often get like a data set with 100 items in it. We're just supposed to make a plot and reassure ourselves about, the parameter estimates. We're not thinking about the real world deployment situation. So this question definitely gets at that. You want to always evaluate it. And humans, this involves humans and human judgment and human preferences and human utilities. So you have to have a role for that. You simply can't write down the utility. You have to be able to make sure that people have a, in the loop kind of role here. So I hope you, really appreciate, these are the wonderful challenges. These aren't the these aren't the ones that say that these ideas are no good to go, or these are the ones that are going to have to be faced by people like us.
Well, Michael, thank you so much. This is a great talk. Hope to invite you come to Purdue in person sometimes in the future. We have such a great honor to have you there, have you here. All right. Thank you so much. I'll probably leave your time to our graduate student. They are looking forward to seeing the big master to teach them what is statistics and those data science is going to be. Thank you so much.
All right. Thank you, Dennis.
Thank you. So thank you, Professor Jordan. Thank you for this excellent talk. So we are going to end this live stream now. Just a second.